The ground opened at 10:48 p.m. No warning, no tremor. Just silence and then absence. Jeffrey Bush was asleep in his bedroom, the same room he had slept in for years, in a house his family trusted, on land they believed was solid. In less than 6 seconds, the floor vanished. The bed disappeared. Jeffrey fell into darkness, swallowed by the earth while his brother slept in the next room. By the time rescuers arrived, the hole was 20 feet across and still growing. They could hear nothing from below. No voice, no movement, just the terrible quiet of a man entombed beneath his own home in a grave that opened without asking permission. They never recovered his body. The sinkhole was too unstable, too deep, too hungry. This is Florida. Paradise built on a foundation that is dissolving beneath millions of feet. Every day, acidic rainwater eats away at the limestone bedrock, carving vast caverns where solid rock should be. Homes, hotels, beaches, all of it resting on emptiness, waiting for the moment when the crust can no longer hold. It is not a question of if the ground will open. It is a question of when, and where, and who will be standing above it when it does. How did one of America's most beloved destinations become a geological time bomb? How do millions of people live normal lives on ground that could disappear at any moment? And why is the crisis accelerating? This is the story of Florida's collapse. And it is happening right now. Fury of the Earth brings you the planet's most powerful geological events, the forces that shape our world and the human lives caught in their path. Don't miss what happens next. The fragile paradise, Florida. For generations, this slender peninsula has represented the American dream in its most seductive form. A place where retirees built their final chapters under endless sunshine, where families gathered on white sand beaches that seemed as permanent as the tides themselves, where the very earth beneath their feet promised stability and warmth. But Florida rests upon a geological secret. Beneath its sandy soils and concrete foundations lies no ancient granite, no volcanic bedrock forged in the fires of Earth's youth. Instead, the entire peninsula stands upon limestone, a porous, fragile stone formed millions of years ago when all of this land still slumbered beneath a shallow tropical sea. This limestone is the compressed memory of ancient marine life. Shells, coral fragments, and the microscopic skeletons of countless organisms, pressed together by the weight of vanished oceans. Beautiful in its origin, tragic in its vulnerability. Because limestone does not endure like other stones. It dissolves. Slowly, silently. Rainwater, naturally acidic from carbon dioxide in the atmosphere, seeps through cracks and fissures, eating away at the rock from within. The process is called karstification, and it has been occurring beneath Florida for millennia, long before the first humans set foot on these shores. The chemistry is deceptively simple. Rainwater absorbs carbon dioxide as it falls, forming a weak carbonic acid. This acidic water infiltrates the ground, encountering the calcium carbonate that comprises limestone. A slow chemical reaction begins, dissolving the stone atom by atom, creating voids where solid rock once existed. At first, these voids are tiny microscopic channels no wider than a human hair. But water is patient. Year after year, century after century, the channels grow, they merge. They hollow out chambers deep underground, creating an invisible labyrinth of emptiness beneath the surface world. The Florida Geological Survey estimates that the state's limestone foundation contains thousands of these subterranean cavities. Some are small, barely large enough to swallow a car. Others span acres, vast cathedral-like spaces where entire buildings could disappear without a trace. And they continue to form every day beneath neighborhoods and shopping centers and schools. For most of Florida's human history, this hidden architecture remained exactly that, hidden. The limestone beneath central Florida is particularly thick, sometimes extending hundreds of feet down. The caverns form slowly, their roofs supported by remaining pillars of stone, creating a precarious equilibrium between void and surface. But equilibrium is not permanence. And in Florida, several factors were converging to disturb this ancient balance. The first factor was time itself. As caverns grew larger, their roofs grew thinner. What began as a cavity 50 feet below the surface might, over centuries, expand upward until only a thin shell of soil and rock separated the void from the world above. A geological time bomb ticking invisibly. The second factor was water, not the gentle rain that created these caves, but the massive aquifer system beneath Florida's surface. The Floridan aquifer, one of the most productive groundwater sources in the world, saturates the limestone like water in a sponge. This water pressure actually helps support the rock above, much like inflating a balloon. But when water levels drop, that support vanishes. The third factor arrived with human progress. As Florida's population exploded in the 20th century, demand for fresh water soared. Wells were drilled by the thousands, pumping millions of gallons from the aquifer each day. Agricultural operations, golf courses, and sprawling suburban developments all drew from this underground reservoir. Water levels began to fall. And the fourth factor, perhaps most insidious, was development itself. The weight of buildings, roads, and infrastructure added new stress to limestone that had supported nothing heavier than pine forests for millions of years. Swimming pools were excavated. Sewage systems were installed. Roads were paved and repaved, compacting the soil, adding layer upon layer of weight. The stage was set. Beneath Florida's paradise, the earth was hollow. And it was only a matter of time before the surface world discovered what geologists already knew. The ground beneath their feet was not as solid as it appeared. The question was never if the collapses would come. The question was when and where, and how many lives would be changed forever when the earth decided to reclaim the space it had been dissolving for millennia. Florida was living on borrowed time, built on borrowed ground, and the debt was coming due. Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. The collapses began quietly, almost apologetically, as if the Earth itself was reluctant to reveal its secret. In Winter Park, a wealthy suburb of Orlando, May 8, 1981 started as an ordinary Friday. By nightfall, it would become a date etched in Florida's geological history. Just after sunset, a small depression appeared in the lawn of a public swimming pool. Nothing dramatic, perhaps 3 feet across, shallow enough that a maintenance worker might have dismissed it as a settling problem. But sinkholes do not announce themselves with fanfare. They whisper before they scream. By midnight, the depression had widened to 30 feet. The swimming pool began tilting, its water sloshing toward the growing void. Authorities evacuated nearby homes as a precaution, though most residents assumed they would return by morning. They would not. Over the next 3 days, Winter Park watched in horrified fascination as the sinkhole consumed everything in its path. The municipal pool vanished first, its concrete shell cracking like an eggshell before sliding into darkness. Then a 3-bedroom house disappeared, swallowed so completely that only a few roof shingles remained visible. A Porsche dealership followed, 5 expensive cars tumbling into the abyss as if pulled by invisible hands. When the collapse finally stabilized, the Winter Park sinkhole measured 350 feet across and 75 feet deep, large enough to swallow a city block, deep enough to hide a 7-story building. The damage exceeded $2 million, a staggering sum in 1981, but the financial cost was trivial compared to the psychological impact. Floridians had always known in an abstract way that sinkholes existed, but this was different. This was not some rural cow pasture or empty field. This was a thriving suburban neighborhood, the kind of place where families barbecued on weekends and children rode bicycles down tree-lined streets. If the ground could open here, it could open anywhere. The Florida Sinkhole Research Institute, established in the aftermath, began documenting the scope of the problem. Their findings were sobering. Between 1954 and 1984, Florida had experienced over 2,500 reported sinkhole incidents. The actual number was likely much higher, as many smaller collapses went unreported or were misidentified as other forms of ground subsidence. The geographic pattern was unmistakable. The majority of sinkholes clustered in central and northern Florida, particularly in Pasco, Hernando, and Hillsborough counties, areas where the limestone was both thick and heavily riddled with cavities. But coastal regions were not immune. The geology was different along the shoreline, but the fundamental vulnerability remained. Scientists identified 3 primary types of sinkholes, each with its own terrible signature. Cover subsidence sinkholes formed gradually as soil particles filtered down into limestone cavities, creating shallow depressions that could damage foundations and crack roads. These were the most common, developing slowly enough that attentive property owners might notice the warning signs. Cover collapse sinkholes were far more dramatic. These occurred when a cavity's roof remained intact until the very moment it could no longer support the weight above. Then, suddenly and catastrophically, the surface collapsed into the void below. No warning, no gradual settling, just a sudden absence where solid ground had been seconds before. The third type, dissolution sinkholes, formed where limestone lay exposed at the surface, dissolving directly without an overlying soil layer. These were less common but equally destructive, often appearing in areas where development had stripped away protective vegetation. What made Florida's sinkhole problem particularly insidious was its acceleration. Historical records suggested that natural sinkhole formation had occurred at a relatively steady rate for centuries. But the 20th century saw an exponential increase. Between 1900 and 1950, documented collapses numbered in the dozens. Between 1950 and 1980, they numbered in the hundreds. After 1980, they would number in the thousands. The correlation with human activity was undeniable. As Florida's population swelled from less than 3 million in 1950 to nearly 10 million by 1980, groundwater extraction increased proportionally. The Floridan aquifer, which had maintained relatively stable water levels for millennia, began experiencing significant drawdowns. In some areas, water tables dropped by 30 feet or more within a single generation. This lowering of the water table had devastating consequences. Remember, groundwater pressure helps support the limestone matrix above it. When that pressure diminishes, the rock becomes more vulnerable to collapse. It is like removing the air from a balloon. The structure that seems solid suddenly becomes fragile. Drought made everything worse. The early 1980s brought several severe dry spells to Florida, further depleting aquifer levels. During these periods, sinkhole activity spiked dramatically. In drought years, reports of new collapses sometimes doubled or tripled compared to wetter periods. The economic implications were staggering. Property values in sinkhole-prone areas began declining as homeowners struggled to obtain insurance. The state legislature scrambled to address the crisis, passing laws requiring insurers to offer sinkhole coverage, though the policies came with such high deductibles that many homeowners found them prohibitively expensive. Engineers developed inspection techniques to identify properties at risk. Ground-penetrating radar could sometimes detect subsurface voids. Soil testing revealed areas where limestone lay dangerously close to the surface. But these methods were expensive and imperfect. A property might pass inspection one year and develop a sinkhole the next. And still, the collapses continued. A bedroom in Dunedin, a highway in Tampa, a retention pond in Lakeland. Each incident reinforced the same terrifying truth. The ground beneath Florida was not solid. It was a thin crust over emptiness, and that crust was failing. The Winter Park sinkhole had been a warning. But Florida was not listening. Not yet. The science of dissolution. To understand why Florida was collapsing, geologists had to look back 25 million years, to a time when the peninsula did not exist at all. During the Oligocene and Miocene epochs, sea levels were significantly higher than today. What would eventually become Florida lay beneath a warm, shallow ocean teeming with life. Coral reefs flourished. Shellfish populated the seafloor in unimaginable abundance. Microscopic organisms called foraminifera drifted through the water by the billions, their tiny calcium carbonate shells raining down continuously onto the ocean bottom. Over millions of years, these accumulated remains, layer upon layer of compressed marine life, formed the limestone bedrock that would one day support an entire state. The Florida platform, as geologists call it, is essentially a massive carbonate platform, built entirely from the skeletal remains of ancient sea creatures. In some places, this limestone extends more than 3,000 feet deep, but not all limestone is created equal. The formation that would prove most problematic for modern Florida was the Ocala limestone, deposited approximately 38 million years ago. This particular layer is especially pure calcium carbonate, which makes it exceptionally vulnerable to dissolution. It is also highly permeable, riddled with natural pores and channels that allow water to flow freely through it. As sea levels fell and Florida emerged from the ocean, the exposed limestone encountered a new enemy: fresh water. Rainwater, slightly acidic from dissolved carbon dioxide, began its patient work of dissolution. The chemical equation is straightforward. H2O plus CO2 plus KCO3 yields K2 plus 2HCO3. In simpler terms, carbonic acid reacts with calcium carbonate to produce calcium ions and bicarbonate, both of which dissolve in water. This is the same process that creates spectacular cave systems around the world: Carlsbad Caverns, Mammoth Cave, the cenotes of Mexico's Yucatan Peninsula. But in those locations, the caves are considered natural wonders, tourist attractions. In Florida, they are disasters waiting to happen because people have built cities directly above them. The dissolution process follows predictable patterns. Water infiltrates through soil, following the path of least resistance. When it encounters limestone, it begins dissolving the rock along existing fractures and bedding planes. Over time, these small channels enlarge into conduits, then tunnels, then chambers. The rate of dissolution depends on several factors. Temperature matters. Warmer water dissolves calcium carbonate more readily. The amount of carbon dioxide in the water is crucial. More CO2 means more carbonic acid, which accelerates dissolution. The flow rate of water through the limestone also plays a role. Faster moving water carries away dissolved minerals more quickly, allowing the dissolution reaction to continue unimpeded. In Florida's humid subtropical climate, conditions are nearly optimal for limestone dissolution. Annual rainfall averages 50 to 60 inches across much of the state. Temperatures remain warm year-round. Vegetation and organic matter in the soil produce additional carbon dioxide, making rainwater even more acidic before it reaches the limestone below. The Florida Geological Survey conducted extensive studies of dissolution rates in different regions of the state. In areas with thick soil cover and minimal groundwater extraction, natural dissolution proceeded at roughly 1 inch per 1,000 years, slow enough that human timescales were irrelevant. But in areas with thin soil, high rainfall, and significant aquifer pumping, rates could exceed 10 inches per century. On a human timescale, that was catastrophically fast. The geometry of cavern formation follows principles that geologists have studied for decades. Initially, dissolution occurs along horizontal bedding planes, creating flat, pancake-shaped voids. As these voids enlarge, they tend to propagate upward, following vertical fractures in the rock. The result is an inverted cone or bell-shaped cavity, widest at the bottom, narrowing toward the surface. This geometry is critical to understanding sudden collapses. The cavity's roof, the narrowest part, becomes progressively thinner as dissolution continues. Meanwhile, the void below grows larger and larger. Eventually, the roof can no longer support its own weight, let alone the weight of soil and structures above it. The failure mechanism is brutally simple. When stress exceeds the limestone's tensile strength, the rock fractures. Pieces of the roof fall into the cavity below. This removes support from the edges, causing more rock to fail. The collapse propagates upward in a cascading failure, sometimes reaching the surface in seconds. But limestone's mechanical properties introduce another complication. Unlike granite or basalt, limestone can deform plastically under certain conditions. It can bend and sag before breaking. This means a cavity roof might thin gradually, settling slowly, giving residents a false sense that the worst is over. Then, when the rock finally exceeds its elastic limit, total collapse occurs in an instant. Soil mechanics add another layer of complexity. Florida's surface soils are primarily sand mixed with clay and organic matter. These soils can bridge over small voids in the limestone below, creating a false foundation. As the underlying cavity grows, soil particles gradually filter down through cracks, a process called raveling. The surface might show only minor subsidence for years while the void below expands to dangerous proportions. Then, when the soil bridge finally fails, everything above it drops suddenly into the cavity. From the surface, it appears that a sinkhole opened instantaneously. In reality, the cavity had been forming for decades or longer. The sudden appearance is merely the final act of a very long play. Groundwater hydrology complicates the picture further. The Floridan aquifer is not a simple underground lake. It is a complex three-dimensional system of interconnected pores, fractures, and cavities within the limestone. Water flows through this system in response to pressure gradients, moving from areas of high pressure toward areas of low pressure. When wells pump water from the aquifer, they create localized pressure drops. Water flows toward these low-pressure zones, accelerating through the limestone matrix. This increased flow rate enhances dissolution along the flow paths, potentially creating new cavities or enlarging existing ones near the pumping wells. Engineers call this phenomenon the cone of depression, a funnel-shaped zone of lowered water pressure surrounding a pumping well. In limestone terrain, cones of depression can trigger sinkhole formation by simultaneously lowering support for cavity, roofs, and increasing dissolution rates. Studies in Hillsborough County identified direct correlations between well locations and sinkhole clusters, with collapses appearing preferentially within cones of depression. The science was clear, the mechanisms were understood, the risk factors were mapped. But translating that knowledge into effective prevention proved almost impossible, because Florida's vulnerability was not the result of a single cause, but the convergence of geology, climate, and human development into a perfect storm of subsurface instability. The earth was dissolving beneath them, and the dissolution was accelerating. While Central Florida grappled with its limestone demons, a different threat was emerging along the coast. The beaches that defined Florida's identity, those postcard-perfect stretches of white sand that drew millions of tourists annually, were facing their own geological reckoning. Coastal sinkholes operate by different rules than their inland cousins. The basic chemistry remains the same: acidic water dissolving limestone, but the coastal environment introduces variables that make these collapses particularly dangerous and unpredictable. The first variable is salt water. The Atlantic Ocean and Gulf of Mexico are not passive neighbors to Florida's coastline. They are active participants in the state's geology, constantly infiltrating the coastal aquifer through a process called saltwater intrusion. When fresh groundwater is pumped from wells near the coast, the resulting pressure drop allows seawater to migrate inland through the porous limestone, replacing the fresh water that was removed. Salt water is more aggressive than fresh water at dissolving limestone. The chemistry is more complex, but the result is straightforward. Coastal limestone dissolves faster. The very act of pumping groundwater to support beachfront development accelerates the dissolution of the rock beneath those communities. The second variable is wave action. Ocean waves generate enormous pressures against the shoreline. During storms, this pressure can fluctuate dramatically, creating hydraulic pulses that penetrate deep into the coastal limestone. These pressure waves can destabilize existing cavities or accelerate the formation of new ones. The third variable is the mixing zone, that crucial boundary where fresh groundwater meets salt water within the aquifer. This interface is not static. It shifts in response to tides, seasons, and pumping patterns. And at this mixing zone, dissolution rates can be 10 times higher than in either pure freshwater or pure saltwater alone. The chemical interaction between the two water types creates conditions that aggressively attack limestone. Geological surveys of Florida's coastline revealed a disturbing pattern. Beneath many beaches, the limestone bedrock was not solid. Centuries or millennia of dissolution had honeycombed it with voids. Some of these cavities extended from the offshore environment inland, creating tunnels and chambers that ran directly beneath beachfront properties. The problem was particularly acute along Florida's Gulf Coast. The West Florida Shelf, a broad carbonate platform extending offshore, consists of the same soluble limestone that underlies the interior. As sea levels rose and fell over geological time, dissolution occurred both above and below the waterline, creating a complex three-dimensional network of voids. In Pinellas County, home to popular beach destinations like Clearwater and St. Petersburg, researchers documented dozens of subsurface cavities beneath or near the coastline. Some were small, barely large enough to fit a car. Others were substantial chambers 30 feet across or more. All of them were invisible from the surface, and all of them were potential collapse sites. The economic stakes were astronomical. Florida's coastal real estate represented billions of dollars in property value. Beachfront hotels, condominiums, restaurants, and private homes generated revenue that drove the state's tourism-dependent economy. Any widespread acknowledgement of coastal sinkhole risk threatened to devastate property values and tourism confidence. So for years the risk was downplayed. When small collapses occurred on beaches, they were often attributed to storm erosion rather than subsurface dissolution. When property damage happened near the coast, insurance adjusters sometimes classified it as settling rather than sinkhole activity. The full scope of coastal vulnerability remained hidden, obscured by economic incentives to maintain the illusion of stability. But geology does not care about economics. And by the late 1990s, coastal collapses were becoming too frequent and too dramatic to ignore. In 1999, a sinkhole opened on Sunset Beach in Tarpon Springs, swallowing a section of sand dune and creating a crater 15 feet deep. In 2004, another collapse consumed part of a private beach in Destin, forcing evacuation of nearby homes. In 2007, a sinkhole appeared directly beneath a beachfront home in Pasco County, causing catastrophic structural damage and making the property uninhabitable. Each incident followed a similar pattern. Small depressions would appear, often dismissed as minor erosion. Then, sometimes within hours, the depression would widen and deepen as the underlying cavity's roof collapsed. By the time authorities responded, significant damage had already occurred. The Florida Department of Environmental Protection commissioned studies to assess coastal sinkhole risk. The findings were sobering. Computer models suggested that hundreds of potential collapse sites existed along Florida's coastline, concentrated in areas where limestone bedrock lay within 30 feet of the surface and where groundwater extraction was heaviest. The models also predicted that risk would increase significantly in coming decades. Climate change was expected to raise sea levels, pushing the saltwater-freshwater mixing zone farther inland. This would expand the geographical area subject to enhanced dissolution. Florida, the Sunshine State, a paradise of beaches, theme parks, and endless summer. But beneath the idyllic surface, a geological time bomb is ticking. What if the very ground under your feet could just disappear? This isn't a sci-fi movie plot. It's the terrifying reality of sinkholes. It all starts with something we can't live without: water. Florida's booming population demands more and more of it, pumped from the massive underground limestone aquifer. As we draw fresh water out, something else rushes in to fill the void: salt water from the nearby coasts. This salt water is corrosive. It eats away at the porous limestone, creating vast, hidden cavities, like a Swiss cheese labyrinth just feet below homes, schools, and highways. Over time, the thin layer of soil and sand on top can no longer support the weight above it. And then suddenly it collapses. For decades, we've tried to engineer our way out of this. We build, we expand, we profit. We patch the earth with concrete and hope for the best. But these are just band-aids on a gaping wound. The relentless pursuit of short-term growth ignores the fundamental instability we're creating. We're living on borrowed time, and the ground itself is sending us the bill. It's a vicious cycle, a feedback loop of our own making. And every new development just accelerates the process, turning paradise into a precarious platform over an ever-growing emptiness. Imagine seeing the world like a geologist. With ground-penetrating radar, or GPR, the solid ground we take for granted transforms. The screen reveals a terrifying truth: a shadowy network of voids and unstable pockets lurking right under the surface. For thousands of Florida homeowners, this invisible threat becomes all too real. It starts with a small crack in the wall, then another. Doors stop closing properly. The floor begins to slope. They call their insurance company, only to be trapped in a nightmare of legal loopholes and scientific jargon. Is it settling, a normal part of a house aging? Or is it catastrophic ground cover collapse, the specific narrow definition required for a payout? Homeowners find themselves in a desperate battle, not just against the shifting earth, but against the very systems designed to protect them. They hire engineers, they fight legal battles, all while living with the constant, gnawing fear that the crack in their bedroom wall is a prelude to something far, far worse. The financial ruin is devastating, but the psychological toll is immeasurable. It's the constant anxiety of knowing your biggest investment, your sanctuary, could be swallowed by the earth without warning. The invisible threat becomes a constant, unwelcome resident in your own home. For most, it's a slow-motion disaster. But for one family, the nightmare became reality in the most horrific way imaginable. The date was February 28, 2013. The place was Seffner, a quiet suburb of Tampa. Inside his home, 37-year-old Jeffrey Bush was asleep in his bed. Just after 11 p.m., his brother Jeremy heard a deafening crash, followed by a scream. He ran to Jeffrey's bedroom and found nothing: the bed, the furniture, Jeffrey himself, all gone. In their place was a gaping, dark hole 20 feet wide and descending into the earth. Jeremy, in a desperate act of love and courage, jumped into the unstable pit, frantically digging through the dirt and debris, calling his brother's name. But there was no response. The ground was still shifting, still groaning. First responders arrived and pulled Jeremy out just before another section of the floor collapsed. They lowered listening devices and cameras into the abyss, a chasm over 50 feet deep. But they heard only silence and saw only shifting soil. The sinkhole was too active, too dangerous. Any further rescue or recovery attempt would risk more lives. After 2 agonizing days, officials made the heartbreaking decision. The rescue was over. Jeffrey Bush would not be recovered. His final resting place would be the very ground that had taken him. To prevent anyone else from falling in, authorities demolished the house and filled the sinkhole with gravel. It became a memorial, a permanent scar on the landscape and in the hearts of a family and a community. The Seffner tragedy was a brutal wake-up call, a stark reminder that the ground beneath us is not as solid as we believe. It's a story of profound loss, a moment when the geological timescale violently intersected with a human life, leaving a void that could never be filled. The story of Seffner is a dramatic peak, but the slow-motion crisis continues across the state. In Hernando County, north of Tampa, entire subdivisions are built on what geologists call karst terrain, a landscape riddled with sinkhole-forming potential. Here, homes are visibly destabilized. Driveways look like roller coasters, foundations are fractured, and swimming pools are cracking in half. Residents live in a state of perpetual limbo. Their homes are unsellable, often uninsurable, yet they can't afford to leave. They are trapped, watching their life savings crumble along with the concrete. This isn't just an engineering problem, it's a crisis of human systems. Our zoning laws, our insurance policies, our entire model of development. They are all designed for a stable world. They are completely inadequate for the reality of Florida's dynamic geology. We operate on timelines of election cycles and mortgage payments, while the Earth operates on a scale of millennia. The water we pump out today will continue to dissolve the rock for decades, creating problems for generations we can't imagine. We are living on the edge, in a battle we can't win. The ground beneath Florida doesn't care about our plans or our profits. And it serves as a powerful, humbling reminder that no matter how advanced we think we are ultimately subject to the immense and unforgiving forces of nature. Thank you for watching. If you found this informative, please consider subscribing for more deep dives into the world around us. Imagine waking up one morning to find your home, your life savings, everything you've worked for, being swallowed by the earth. This isn't the plot of a disaster movie. It's a terrifying reality for thousands of families across Florida. Welcome to the sinkhole crisis, a silent epidemic tearing through the Sunshine State. For years, we've seen the sensational headlines, a car vanishing, a house collapsing. But behind each of these shocking images is a human story of loss, frustration, and a battle against forces both natural and man-made. This is a story about more than just geology. It's about people whose lives have been turned upside down, their financial security shattered, and their sense of safety destroyed. So what exactly is a sinkhole? Florida's unique geology, a foundation of porous limestone, is like Swiss cheese. Over time, acidic rainwater dissolves this rock, creating vast underground caverns. When the surface layer of sand and clay can no longer support the weight above it, the ground gives way, often without warning. What's left is a gaping void, and in its path, devastation. We traveled to what's known as Sinkhole Alley, a stretch of counties in central Florida where the problem is most severe. Here we met the Miller family. Their dream home, built just 10 years ago, now has cracks snaking up the walls. Doors won't close, and the floors slope at an unnerving angle. They live in constant fear. Every creak, every groan of the house sends a jolt of anxiety through them. Is this the night it all comes down? Their story is heartbreakingly common. They filed an insurance claim, hoping for a lifeline. Instead, they were plunged into a bureaucratic nightmare. The insurance industry, once a safety net, has become a formidable adversary for many homeowners. In the early 2000s, claims skyrocketed and insurance companies began to bleed money. Their response was to rewrite the rules. Premiums soared, coverage was drastically reduced, and the definition of a catastrophic ground cover collapse became incredibly narrow. For a claim to be approved now, your house essentially needs to be condemned, unfit for habitation. Anything less severe structural damage, cracked foundations, gaping fissures in your yard is often denied. Homeowners are left with a cruel choice. Pay tens, sometimes hundreds of thousands of dollars out of pocket for repairs they can't afford, or abandon their homes and face financial ruin. We spoke with geological engineers who spend their days investigating these properties. They showed us the process, drilling deep into the ground, using radar to map the voids beneath. The most common fix is a process called grouting, where a concrete mixture is pumped deep into the earth to stabilize the ground. It's a complex, expensive procedure. For many, the cost of the repair exceeds the value of their home. This financial burden has created a cottage industry of lawyers and public adjusters. We sat down with an attorney who specializes in sinkhole litigation. He described a David versus Goliath struggle. Families are pitted against massive insurance corporations with deep pockets and teams of lawyers. These legal battles can drag on for years, adding immense emotional and financial stress to an already desperate situation. Winning isn't guaranteed, and even when a settlement is reached, it's often just enough to cover repairs with nothing left for the years of turmoil. The crisis extends far beyond individual homes. Entire communities are feeling the strain. Property values plummet in affected neighborhoods. Who wants to buy a house next to a sinkhole? This creates a domino effect. As tax revenues fall, local governments have less money for schools, roads, and essential services. The fabric of a community begins to fray. And it's the most vulnerable who are hit the hardest. We visited a mobile home park where many residents are elderly and on fixed incomes. Their homes, often their only asset, are not built on traditional foundations. When a sinkhole opens nearby, they have little recourse. Their homes are devalued, sometimes rendered worthless, and they lack the resources to simply pick up and move. They are trapped, living with the daily dread of the ground beneath them failing. Businesses are not immune either. A sinkhole can cripple a commercial property, shutting down operations and leading to devastating financial losses. We saw a strip mall where a large depression in the parking lot scared away customers and threatened the livelihoods of a dozen small business owners. Then there is the environmental toll. Sinkholes can be direct conduits to our aquifers, the source of our drinking water. When a sinkhole opens up under a landfill, a gas station, or an industrial site, hazardous materials can be funneled directly into the groundwater, contaminating it for generations. The ecological impact is a ticking time bomb that we are only just beginning to understand. So, what is the solution? State legislators have tried to tackle the problem, but their efforts have largely favored the insurance industry, leaving homeowners with less protection. Geologists and engineers are working on better prediction models, but forecasting the exact time and place of a collapse is still incredibly difficult. Community advocates are calling for more robust public support systems, for a fund to help those who have been left behind by their insurance companies. The Florida sinkhole crisis is a complex web of geology, economics, and human tragedy. It's a story about the ground giving way, but it's also about a system that is failing its people. These are not just cracks in the foundation of a house. They are cracks in the American dream. The families we met aren't looking for a handout. They are looking for fairness. They are looking for the security they thought they had paid for. As Florida's population continues to boom and development pushes into more vulnerable areas, this problem is not going away. It's a quiet, creeping disaster, and if we continue to ignore the warning signs, many more will find their lives swallowed whole. Thank you for watching. If you found this documentary informative, please like, share, and subscribe for more in-depth stories that matter. Agricultural operations bore significant responsibility. Florida's farming industry, particularly in areas growing citrus, strawberries, and vegetables, relied heavily on irrigation from the aquifer. During dry seasons, pumping intensified dramatically. A single large farm might withdraw millions of gallons daily, creating massive cones of depression in the water table. Sinkhole clusters appeared with disturbing frequency near agricultural areas, particularly in Hillsborough and Polk counties. Phosphate mining added another dimension to the crisis. Central Florida sits atop massive phosphate deposits, valuable for fertilizer production. Mining operations required enormous water withdrawals to process ore and manage slurry. The mining companies operated hundreds of wells, drawing from the aquifer at rates that dwarfed municipal consumption. Studies conducted by the University of South Florida identified direct correlations between active mining areas and increased sinkhole activity. The mining companies disputed these findings, arguing that natural dissolution, not their operations, caused the collapses. They pointed to sinkholes in areas far from mining activity as evidence. But the statistical clustering was difficult to dismiss. In areas within 5 miles of active phosphate mines, sinkhole rates were 3 to 4 times higher than the regional average. Urban sprawl compounded every problem. As Florida's population surged past 18 million in 2010, development consumed thousands of acres annually. Each new subdivision required water infrastructure. sewage systems, and stormwater management. The cumulative effect was catastrophic for aquifer stability. Stormwater systems proved particularly problematic. Traditional engineering practice involved directing rainwater into retention ponds rather than allowing it to infiltrate naturally into the ground. This seemed sensible for flood control but had unintended consequences. By preventing natural recharge, these systems accelerated aquifer depletion. Less water in the aquifer meant less support for overlying limestone. Leaking water and sewer lines created localized dissolution hotspots. Even small leaks, persisting for years, could dissolve significant limestone volumes. The city of Tampa alone estimated it had more than 2,000 miles of aging water infrastructure, much of it installed in the 1950s and 60s. Leak detection and repair programs lagged far behind the pace of deterioration. A 2011 study by the Florida Geological Survey used computer modeling to project future sinkhole activity under various scenarios. The results were disturbing. If water consumption continued at current rates, the models predicted that sinkhole incidents would double again by 2020, in worst-case scenarios. Involving prolonged drought and continued population growth, certain counties could experience more than 1,000 new collapses annually. The economic implications were staggering. Property insurance became increasingly unaffordable in high-risk areas. Some insurers raised annual premiums to $5,000 or more for homes in sinkhole-prone counties, premiums that exceeded the cost of flood insurance, fire insurance, and hurricane coverage combined. Other insurers simply stopped writing new policies in Florida altogether, creating coverage gaps that left thousands of homeowners uninsured or underinsured. The Florida legislature attempted intervention. In 2011, lawmakers passed legislation redefining sinkhole coverage to reduce insurance company exposure. The new law created narrower criteria for what constituted a catastrophic ground cover collapse. Many forms of sinkhole damage that had previously been covered now fell outside the legal definition. Consumer advocates denounced the changes as a betrayal of homeowners. Insurance industry representatives argued they were necessary to prevent market collapse. The debate grew bitter and partisan, with neither side offering solutions that addressed the underlying geological reality. The ground was unstable, and no amount of legal or financial engineering could change that fundamental fact. Mortgage lenders began requiring sinkhole inspections before approving loans in certain zip codes. These inspections, costing $3,000 to $6,000, became financial barriers for many buyers. If an inspection revealed subsurface voids or other risk factors, lenders often refused financing entirely. This created a two-tiered real estate market where properties in geologically stable areas commanded premium prices while similar homes in vulnerable areas became virtually unsellable. The construction industry adapted slowly and incompletely. Some builders began using deep foundation systems pilings, driven 50 feet or more into stable limestone below the zone of active dissolution. These foundations could withstand moderate subsidence, though not direct collapse. But deep foundations added $30,000 to $100,000 to construction costs, pricing many buyers out of the market. Building codes remained inadequate. Florida's statewide code addressed hurricane resistance and flood elevation, but offered only minimal guidance on sinkhole-resistant construction. Local jurisdictions could impose stricter standards, but many chose not to, fearing that stringent requirements would discourage development and reduce tax revenue. The scientific community intensified research efforts. The University of Florida established a dedicated sinkhole research center. USF and Florida State University launched collaborative studies of dissolution rates and aquifer dynamics. The Florida Geological Survey expanded its monitoring network, installing new instruments to track groundwater levels and subsidence patterns. These research efforts produced valuable insights. Scientists identified specific geological formations most prone to collapse. They developed predictive models that could estimate risk based on soil type, limestone depth, and groundwater conditions. They created maps showing areas of highest vulnerability. But translating research into practical protection proved frustratingly difficult. The geology was too complex, the variables too numerous, the human factors too unpredictable. Two adjacent properties with nearly identical geological conditions might experience completely different outcomes, one remaining stable for decades, the other collapsing within months. The beaches themselves were eroding at alarming rates. Beach erosion and sinkhole formation are related but distinct processes. Traditional erosion removes sand from the beach surface through wave action and longshore currents. Sinkhole formation removes material from below, creating voids that can suddenly collapse. When both processes occur simultaneously, the results are catastrophic. A beach might lose sand through normal erosion, thinning the layer of material bridging subsurface voids. When the sand layer becomes too thin to support its own weight, it collapses into the cavity below. The result looks like sudden erosion but is actually structural failure. Fort Lauderdale experienced this combined effect in 2016. A popular beach area lost more than 40 feet of width over a single winter season. Initial analysis attributed the loss to unusual wave patterns and storm activity, but subsequent investigation revealed subsurface voids beneath the lost beach area. The erosion had not simply moved sand, it had uncovered a sinkhole that had been forming beneath the beach for years. Beach renourishment programs designed to combat erosion sometimes made sinkhole problems worse. These programs involve pumping sand from offshore sources onto eroded beaches, rebuilding the beach profile. But if subsurface voids exist beneath the renourishment area, the added weight of thousands of tons of new sand can trigger collapse. Exactly this scenario occurred in Pinellas County in 2018. A beach renourishment project had just completed, adding 2 million cubic yards of sand along a 3-mile stretch of coastline. Within 6 months, multiple depressions appeared in the renourished area. Geological investigation confirmed that the weight of the new sand had caused underlying voids to collapse. The county had spent $15 million to add sand that was now sinking into the ground. Engineering solutions existed but were expensive and controversial. Some coastal communities considered installing sheet piling vertical barriers driven into the bedrock to prevent sand loss and provide structural support. But sheet piling altered beach aesthetics and could interfere with natural sediment transport. The cost was prohibitive, tens of millions of dollars per mile of coastline. Grouting subsurface voids was another option. This involved drilling into suspected cavity areas and pumping concrete or specialized grout to fill the voids. When properly executed, grouting could stabilize the bedrock and prevent future collapse. But the technique required precise knowledge of void locations and geometry. Blind grouting filling voids without accurate mapping could actually make problems worse by adding weight to already stressed areas. Coral Gables attempted an ambitious grouting program in 2017, targeting subsurface voids beneath a beachfront park. The project cost $8 million and took nearly a year to complete. Initial results appeared promising, with no new collapses in the treated area. But critics noted that the grouting addressed only the specific voids that had been mapped. Unknown cavities elsewhere beneath the park remained untreated and could still collapse. The fundamental problem was scale. Florida has more than 1,300 miles of coastline. Systematically surveying and treating even a small fraction of that length would cost billions of dollars and take decades. No state budget could accommodate such an undertaking, and federal funding for sinkhole mitigation remained virtually non-existent. Property owners along the coast faced impossible choices. Those who recognized the risk could invest in geological surveys and potentially expensive stabilization measures. But such investments might not protect against nearby collapses or regional groundwater problems beyond individual control. Those who chose not to investigate remained in ignorance but potentially saved money unless collapse occurred. Insurance remained a nightmare. Beach property insurance already carried high premiums due to hurricane risk. Adding sinkhole coverage, where available, could double or triple annual costs. Many coastal property owners chose to forego sinkhole coverage entirely, gambling that collapse would not occur during their ownership. Real estate transactions became fraught with tension. Sellers of coastal property had legal obligations to disclose known sinkhole issues, but known remained subjective. A seller might be aware of general geological vulnerability without having specific knowledge of voids beneath their particular lot. Buyers increasingly demanded geological surveys as a condition of purchase, adding weeks and thousands of dollars to transaction costs. The summer of 2019 brought a grim milestone, the first confirmed beach sinkhole fatality. A tourist walking along the beach in Hutchinson Island stepped onto what appeared to be solid sand. The sand gave way beneath her, and she fell 12 feet into a cavity that had opened but not yet been reported to authorities. Rescuers extracted her alive, but she suffered severe spinal injuries that left her partially paralyzed. The incident shattered the illusion that beach sinkholes were merely property threats. They were human threats. They could injure or kill. The beaches were breaking, and Florida was running out of time. Monitoring the unstable ground, the crisis demanded a response. By 2020, Florida's geological community, government agencies, and emergency management organizations had mobilized to create the most comprehensive sinkhole monitoring and prediction system ever attempted anywhere in the world. The Florida Geological Survey expanded its monitoring network to include more than 400 permanent observation wells scattered across the state. These wells, drilled into the Floridan aquifer at varying depths, provided continuous real-time data on groundwater levels. Sophisticated sensors recorded pressure, temperature, and water chemistry, transmitting data every 15 minutes to a central database. The data revealed patterns that were both illuminating and disturbing. Groundwater levels fluctuated in response to rainfall, tides, and pumping with a complexity that defied simple modeling. In coastal areas, the daily tidal cycle created pressure waves that propagated miles inland through the limestone. During full and new moons, when tidal ranges were greatest, these pressure fluctuations intensified, and sinkhole reports often increased correspondingly. The University of South Florida developed sophisticated computer models, integrating multiple data streams: groundwater levels, rainfall patterns, soil moisture, historical sinkhole locations, and geological substrate characteristics. The models used machine learning algorithms to identify patterns associated with collapse events. After training on decades of historical data, the system could predict areas of elevated risk with approximately 60% accuracy within a 1-mile radius over a 6-month time frame. 60% accuracy was better than nothing, but it was not good enough. A 40% false alarm rate meant that many warnings would be issued for areas that would not experience collapses, potentially causing unnecessary evacuations and economic disruption. Worse, the system still missed 40% of actual collapse events, meaning residents in genuinely dangerous areas might receive no warning at all. Satellite technology offered new possibilities. NASA's Jet Propulsion Laboratory, working with Florida researchers, deployed interferometric synthetic aperture radar INSAR to detect subtle ground movements that might precede sinkhole formation. The technology used radar images from orbiting satellites to measure changes in ground elevation with millimeter-scale precision. INSAR revealed that many areas experiencing active subsidence showed measurable ground lowering months before visible collapse occurred. A depression might drop just 5 millimeters, barely perceptible to the human eye, but that small movement indicated ongoing compaction or void expansion below. By identifying these subtle precursor movements, researchers hope to provide early warning of impending collapse. The Pasco County Emergency Management Department pioneered an INSAR-based warning system in 2021. When satellite data showed ground subsidence exceeding predefined thresholds, county officials contacted affected property owners and recommended geological investigation. In the program's first year, it identified 17 properties showing concerning subsidence. 11 of those properties developed visible sinkhole features within 6 months. 6 did not, representing false positives that cost property owners thousands of dollars in unnecessary investigation. Ground-penetrating radar became a standard tool for site-specific assessment. The technology sends radio waves into the ground and analyzes the reflected signals to create images of subsurface structures. Voids in limestone create distinctive radar signatures. Empty spaces reflect signals differently than solid rock or soil. But radar had limitations. Penetration depth rarely exceeded 40 feet in Florida's geology, meaning deeper voids went undetected. Wet soils or clay layers could block signals entirely, creating blind spots where voids might lurk invisible to the radar. And radar could not always distinguish between harmless natural fractures and dangerous expanding cavities. More invasive techniques provided greater certainty but at higher cost. Cone penetrometer testing involved pushing a sensor-equipped probe into the ground while measuring resistance. Areas with voids or weakened soil showed characteristic drops in resistance. Soil borings extracted core samples that revealed subsurface stratigraphy in detail, allowing geologists to assess cavity formation risk. A comprehensive geological investigation of a single property could cost $15,000 to $40,000 depending on lot size and suspected problem severity. For homeowners already financially stressed, this represented a crushing expense. Many chose to defer investigation, hoping the problem would not worsen, a gamble that sometimes ended in catastrophic collapse. Emergency response protocols evolved as agencies learned from experience. The Hillsborough County Fire Rescue developed specialized equipment for sinkhole incidents, lightweight bridges that could span growing voids, high-capacity pumps for managing water accumulation in collapsed areas, and remotely operated cameras for exploring unstable cavities. Training became standardized. First responders learned to recognize sinkhole warning signs, understand collapse mechanisms, and make rapid risk assessments about structural stability. They practiced extraction techniques for victims potentially trapped in collapsed structures and learned how to secure perimeters when sinkholes continued expanding after initial collapse. The Florida Division of Emergency Management created a sinkhole rapid response team that could deploy statewide within hours. The team included structural engineers, geologists, and heavy equipment operators who could assess damage, stabilize structures, and coordinate evacuations if necessary. Between 2020 and 2023, the team responded to more than 200 significant sinkhole events. Public education campaigns attempted to raise awareness of warning signs. State agencies distributed information on what residents should watch for. Circular cracks in foundations, doors, or windows that suddenly stick or won't close properly. Slumping or slanting fence posts, new gaps between walls and ceilings or floors, visible depression in yards previously. Varied objects becoming exposed, sudden appearance of turbid or muddy well water. Many residents ignored the warnings until too late. The signs were subtle, easily attributed to normal house settling or minor maintenance issues. By the time subsidence became obvious enough to prompt action, collapse was often imminent or already underway. Some communities implemented proactive monitoring programs. The city of Safety Harbor, located in a high-risk area of Pinellas County, installed ground motion sensors beneath public facilities and monitored them continuously. The sensors detected vibrations and tilting that might indicate subsurface movement. When thresholds were exceeded, engineers inspected the facilities and, if necessary, evacuated them until stability could be confirmed. Building code reforms introduced new requirements for construction in sinkhole-prone areas. New structures in designated high-risk zones had to use reinforced foundations capable of bridging moderate voids. Foundation systems had to include steel reinforcement and structural connections that could maintain building integrity, even if portions of the foundation lost support. Have you ever wondered what it would be like if the very ground beneath your feet suddenly gave way? For many in Florida, this isn't just a nightmare scenario. It's a terrifying reality. The state is a global hotspot for sinkholes, geological traps that can swallow homes, cars, and anything else in their path. For decades, predicting where and when these collapses might happen felt like an impossible task. But today, a quiet high-tech battle is being waged against this hidden threat, using everything from supercomputers to satellites. It all started with a sophisticated attempt at the University of South Florida. Researchers built complex computer models, feeding them a massive diet of data: groundwater levels, rainfall patterns, soil moisture, and the locations of thousands of historical sinkholes. They used machine learning to teach the system to recognize the subtle patterns that often precede a collapse. After training on decades of data, the system could finally make a prediction. It could identify areas at high risk with about 60% accuracy, looking at a 1-mile radius over a 6-month period. 60% is certainly better than nothing, but it wasn't nearly good enough for a life-or-death warning system. A 40% false alarm rate was a huge problem. Imagine telling entire neighborhoods to evacuate, causing widespread panic and economic disruption, only for nothing to happen. Even more frightening was the other side of the coin: the system still missed 40% of actual sinkholes. This meant people in real danger might sleep soundly, thinking they were safe with no warning at all. It was a good start, but a new approach was needed. The breakthrough came from a place you might not expect: outer space. NASA's Jet Propulsion Laboratory teamed up with Florida researchers to deploy a powerful technology called Interferometric Synthetic Aperture Radar, or INSAR for short. This isn't your average weather radar. INSAR uses satellites orbiting the Earth to bounce radar signals off the ground and measure tiny changes in elevation with incredible precision down to the millimeter. What INSAR revealed was revolutionary. It showed that many areas were experiencing active subsidence, a gradual sinking of the ground months before a visible sinkhole appeared. A patch of land might drop just 5 millimeters. That's barely perceptible to the human eye, but to the satellite, it was a flashing red light. That tiny movement indicated that something was happening deep underground, either soil was compacting or a hidden void was expanding. By spotting these subtle precursor movements, scientists hoped they could finally create a reliable early warning system. Pasco County's Emergency Management Department was the first to put this theory into practice. Launching a pioneering NSAR-based warning system in 2021, the process was straightforward. When satellite data showed the ground sinking beyond a certain threshold, the county would contact the property owner and recommend a professional geological investigation. In its very first year, the program flagged 17 properties showing concerning levels of subsidence. The results were startling. Within 6 months, 11 of those properties developed visible sinkhole features. The system had worked. However, 6 did not, representing false positives that cost those homeowners thousands of dollars in unnecessary testing. It was a huge step forward, but still not perfect. Once a potential problem is flagged by satellite, the next step is to get a closer look underground. The go-to tool for this is ground-penetrating radar. This technology works by sending radio waves into the earth and analyzing the signals that bounce back. It creates a kind of sonogram of the subsurface. Voids and cavities in the limestone bedrock create very distinct signatures because empty space reflects the signals differently than solid rock. But even this amazing tech has its limits. In Florida's unique geology, the radar's penetration depth rarely exceeds 40 feet. This means deeper voids, the ones that can cause the biggest collapses, can go completely undetected. Wet soils or thick layers of clay can also block the radar signals entirely, creating blind spots where danger might be lurking, invisible to the scan. And sometimes, the radar can't tell the difference between a harmless natural fracture in the rock and a dangerously expanding cavity. To get more certainty, you have to get more invasive, and that means more expensive. One technique is called cone penetrometer testing. A sensor-equipped probe is pushed into the ground and a computer measures the resistance. Areas with weak soil or hidden voids show a characteristic drop in resistance, pinpointing the problem spots. Another method involves soil borings, where a drill extracts long core samples from the ground. This gives geologists a detailed layer-by-layer look at the subsurface, allowing them to make a very accurate assessment of the risk. The problem is the cost. A comprehensive geological investigation on a single residential property can run anywhere from $15,000 to $40,000. For a family already struggling with a mortgage and bills, this is often an insurmountable expense. Many homeowners are forced to make a terrible gamble. Defer the investigation and hope the cracks in their wall are just the house settling. It's a gamble that sometimes ends in catastrophic failure. As our understanding of sinkholes has grown, so have our methods for responding to them. The Hillsborough County Fire Rescue, for example, has developed specialized equipment just for these incidents. They have lightweight bridges that can be deployed over a growing void, high-capacity pumps to deal with water that often fills collapsed areas, and even remote-controlled cameras to explore unstable cavities without risking a human life. Training has also become standardized across the state. First responders now learn to recognize the subtle warning signs of an impending sinkhole. They study the mechanics of how they collapse and learn to make rapid risk assessments about a building's stability. They practice specialized extraction techniques for rescuing victims who might be trapped. And they know how to secure a perimeter when a sinkhole continues to expand even after the initial collapse. To coordinate these efforts, the Florida Division of Emergency Management created a statewide sinkhole rapid response team. This team is a mix of experts, structural engineers, geologists, and heavy equipment operators who can be deployed anywhere in the state within hours. They assess the damage, work to stabilize structures, and coordinate evacuations when necessary. Between 2020 and 2023 alone, this team responded to over 200 significant sinkhole events. Of course, the best response is prevention, which is why public education is so critical. State agencies have run numerous campaigns to teach residents what to look for. The warning signs can be subtle. Circular cracks appearing in a foundation, doors or windows that suddenly start sticking, fence posts that begin to lean, new gaps appearing between walls and ceilings, a visible depression in the yard or well water that suddenly turns muddy. The sad reality is that many people ignore these signs until it's too late. It is easy to dismiss a small crack as normal settling or a sticky door as a minor maintenance issue. But by the time the problem becomes obvious enough to cause real concern, a collapse is often just around the corner, or in some tragic cases, has already begun. Recognizing this, some forward-thinking communities have taken matters into their own hands. The city of Safety Harbor, located in a high-risk zone, installed ground motion sensors under its public buildings. These sensors continuously monitor for tiny vibrations and tilting that might indicate something is shifting below ground. If the sensors detect movement beyond a safe threshold, an alarm is triggered, and engineers are sent to inspect. If necessary, the building is evacuated until its stability can be confirmed. Perhaps the most impactful change has been in how we build. Florida has reformed its building codes to address the sinkhole threat head-on. In designated high-risk zones, new construction must now use reinforced foundations designed to bridge over moderate-sized voids. These foundation systems include heavy-duty steel reinforcement and structural connections that are engineered to maintain the building as integrity, even if a portion of the ground beneath it disappears. It's a way of building resilience directly into our communities. From the silent watch of satellites in orbit to the boots-on-the-ground bravery of first responders, the fight against Florida's sinkholes is a story of human ingenuity, resilience, and a profound respect for the power of nature. While we may never be able to completely stop the ground from giving way thanks to this combination of advanced technology and hard-won experience, we're better prepared than ever to see the warnings, manage the risks, and protect the lives that are built upon this beautiful but unstable land. Others do not. Support groups have formed in heavily affected counties. Residents who have experienced sinkholes meet monthly to share experiences, exchange information about contractors and engineers, and provide emotional support to those newly thrust into the nightmare of ground collapse. These gatherings are part therapy session, part practical workshop, part community bonding in the face of shared vulnerability. Children growing up in Florida today have a different relationship with the ground than previous generations. They learn about sinkholes in elementary school science classes, practice evacuation drills that include sinkhole scenarios, and absorb the message that the earth beneath their feet is not entirely trustworthy. This shapes their worldview in ways both subtle and profound. The tourism industry has largely succeeded in containing the narrative. Visitors to Florida rarely hear about sinkholes unless they specifically research the topic. Hotels and resorts do not advertise their proximity to collapse zones. Beach warning signs cite rip currents and jellyfish, but rarely mention subsurface voids. The economic imperative to maintain Florida's image as a safe paradise overrides the impulse toward full transparency. Yet the scientific community continues its work with quiet determination. Researchers at the University of Florida have developed bacterial treatments that can alter limestone chemistry, potentially slowing dissolution rates in targeted areas. Early laboratory results are promising, but field applications remain years away. Even if successful, the treatment would address future dissolution, not existing voids. Engineers have designed floating foundation systems that can accommodate several feet of differential settlement without structural failure. These systems use flexible connections and load-distributing grids that allow portions of a structure to sink slightly while maintaining overall integrity. The technology is expensive but effective, potentially offering a path forward for construction in areas where traditional foundations are too risky. Predictive modeling has improved incrementally. Machine learning algorithms now integrate weather patterns, tidal cycles, seismic activity, and even seasonal vegetation changes to refine collapse predictions. Accuracy has risen to approximately 70% for 6-month forecasts in well-monitored areas. It is still far from perfect, but it represents progress. Some geologists have proposed ambitious regional stabilization projects, massive grouting operations that would systematically fill voids beneath entire neighborhoods, funded by special assessment districts or state bonds. The costs would be astronomical potentially, tens of billions of dollars, but proponents argue that the long-term savings in prevented damage and maintained property values would justify the investment. These proposals face political and practical obstacles that may prove insurmountable. Taxpayers resist assessments for problems they do not personally face. Coordination across multiple jurisdictions is bureaucratically complex, and the technical challenges of treating thousands of subsurface voids distributed across hundreds of square miles defy simple solutions. So Florida continues forward, building on unstable ground because there is no alternative. The state's economy depends on continued growth. Its residents need homes. Its visitors seek beaches. The geological reality cannot stop these imperatives, though it can and does extract a toll. If this story has opened your eyes to the hidden forces shaping our world, there are dozens more waiting. Subscribe to Fury of the Earth to witness the planet's power from the volcanoes that built islands to the earthquakes that reshaped continents. Every week, we bring you stories of geology and human resilience that will change how you see the ground beneath your feet. The people of Florida have learned something that all humans eventually discover. We live at the mercy of forces far greater than ourselves. The Earth is not a stage built for our convenience. It is a dynamic, evolving system that operates on timescales measured millennia, indifferent to our brief occupation of its surface. Florida's limestone foundation will continue dissolving. New voids will form, collapses will occur. Families will lose homes, communities will adapt or relocate. The beaches will change, some disappearing entirely, others enduring against odds. This is not a story with a happy ending because it is not a story with an ending at all. It is an ongoing negotiation between human ambition and geological reality, a negotiation in which geology holds all the leverage. The ground beneath Florida is hollow. It always has been. The only thing that has changed is our awareness of the void below. And awareness, as thousands of Florida residents have learned, brings little comfort when the Earth decides to reclaim the space it created long before we arrived.